All right, so we're recording, and yeah, welcome everybody. We're going to go ahead and get started. I know some people are still filing in from the field, but we're super excited to have geologists from William and Mary here, and they're going to be talking about the
Very.
geology, the Catoctin Formation here at Montpelier, but then also in particular some of the crystal studies that Marina's doing on the memorial site. So Dr. Chuck Bailey, who is of Virginia, is from Lava's fame, is going to be discussing the Catoctin Formation today. Also, we have Dr. Clem Hamelin, say your name correctly. Okay, who's here. And then Marina, what's your last name, Marina? Marina Ashurkoff, who is actually, it's your your thesis study, your senior thesis. She's writing her senior thesis on the quartz crystals from the Catoctin Formation that we discovered from the memorial site. So we're super excited. So, and on screen we've got Diane and Henry. Hello, Diane. How are you doing? Representing Chicago there.
Everybody, I'm fine,
Hello.
thanks. I hope everyone's well.
We are. Thanks, Diane. So, Chuck, do you want me to go ahead and get the PowerPoint started? That sounds great. So let me share screens on Zoom here. Share screens. And I'm going to hide meeting controls. And And then what I'm going to do is duplicate slideshow. Yeah, and this should get you where you need. And you get the you can sit right here, Chuck, and you've got the mouse that you can advance with. And I'll move my thing here.
All right. Awesome. Well, I'm excited to see everyone in the room. Looks like you guys were doing real work today. We basically sat on our butts and drove up from Williamsburg, but we are going to do some field work this afternoon. So I just wanted to take a time to thank Matt for having us, and it's exciting to see this big cohort. So yeah, so I'll get rolling. My job today is to give you a little bit of an introduction to the geology around Montpelier and in Virginia, and then I'm going to hand it over to Marina, who's going to talk about effectively their senior research, which is truly focused on, quartz from right here at Montpelier. So, yeah, this is a blown up map of Virginia. And what you can see here are Virginia's sort of five geologic provinces. And if you're from Virginia, you may have had to learn about these in elementary school. But if you're not from Virginia, maybe this is sort of new to you. So, what is cool about Virginia is that it has pretty distinctive geology. And we go from the mountains to the coast, to the coast to the mountains, as we kind of did today. And on this map, you'll see a red star, and that is effectively our location here at Montpelier. We are truly on the boundary between what geologists refer to as the Blue Ridge province and the Piedmont. Even the landscape is more rolling and not particularly mountainous, and there's some subtleties there. But this is a region where there's a very, very long geologic history, and that's one of the things that I get to do as a geologist at William Mary is explore that. So, to give you a sense of how we explore this, at William Mary, we are very active in doing sort of community field trips. And so, here is a photograph from our department field trip last September to Shenandoah National Park. And the reason I wanted to show this is Marina is somewhere in the photograph. There you are. And on our ride to Shenandoah National Park, we actually stopped here at Montpelier. And that was a stop because late last summer, Matt sent me pictures of these weird quartz crystals and said, dude, can you help me out here? And I was like, dude, I'm not sure I can. But we decided to show up, and Marina was enraptured with the quartz crystals. And that is kind of how this project got started. And that to me is one of the special things about sort of being a geoscientist is that as I get older and older, I take more and more joy in like working with a variety of other scientists and others there. Tomorrow I'm going to be with some other We Marry Geo students, and we're going to be at Jamestown looking at weird rocks at Jamestown. So there's kind of a theme there. The other thing I want to hit on here is almost any time you go to the field, there is so much that you can see. And to me, this is all geoscience. So you guys are archaeologists, maybe anthropologists, but I guess my my soapbox message is if you have an opportunity to take an earth science class, do, because there's so many connections. A lot of people think that geology is just about rocks. And we're going to talk to you about rocks and minerals today, but it's a lot more than that. So on this particular field trip, we were talking about the weather. All right. So there's a temperature inversion in the Shenandoah Valley. Um, in the Blue Ridge Mountains proper, these forests have endured acid rain for a few generations. And actually, the bedrock either amplifies that or mutes that as far as how things go. And so it's all around you, and that's one of the cool things about being a geoscientist. All right. The other thing, I think Matt would like us to try to teach you something. So I'm going to try. I'm not going to maybe try very hard. When we come to thinking about earth materials, geologists would classify earth materials into one of three kinds of rocks: igneous rocks, sedimentary rocks, and metamorphic rocks. And the other thing about Virginia is we've got all of them. You want a rock? We got pretty much all of it here in Virginia. Um, and in fact, just here on the property at Montpelier, there are igneous rocks that have been metamorphosed, so they've gotten a little both. And there are also sedimentary rocks that are exposed here. So just underfoot, if you wander around, you'll be able to see things. Obviously, there's a treasure trove of samples that have come in from the outside today, and maybe we can talk about those. All right, so we got that. And so let's set a little more of the regional picture here. About 30 miles to the west are the Blue Ridge Mountains. And some of the most famous or exciting places in Shenandoah National Park include Hawksbill Mountain, which is labeled there, as well as Old Rag Mountain, which is quite rocky. And the rocks in the Blue Ridge are amongst the oldest rocks in Virginia. And one of the things that we oftentimes do is try to figure out how old are these things. And so I just wanted to give you an introduction to how we would go about that. So Old Rag Mountain is made primarily of a granite, very distinctive looking granite. And Marina, can you pass around that sample of sort of Blue Ridge granite that we brought so everyone can put their hands on it? And so here's a picture of the Old Rag granite. There's a sample of a similar rock going around there, and you can see the white feldspars, which is a particular mineral. There's blue, gray quartz in these rocks. But a lot of times people want to know, how old are these rocks? And we have ways to answer that. And that is because there are certain minerals that form in granites, like the mineral zircon here. And zircon is a zirconium silicate. And if you look on the picture on the right, ooh, I have a laser pointer. Picture on the right. Now, to give you a sense of scale, that's a human hair. So typically what we would do, if you collect a sample of granite, you can crush it up and actually separate out the individual grains of zircon. And these zircon grains actually incorporate a little bit of uranium when they form. And that is an unstable isotope. So over time, that uranium decays to lead, and that allows us to potentially figure out when these zircons and the rock actually formed. So we're not going to turn this into a full-on geochemistry lesson. But what we ultimately do with these zircons is we put them into a mass spectrometer, and we volatilize them with a laser. And the gas that comes off is going to basically contain a certain amount of uranium, a certain amount of lead, and from that, we can determine when the crystal formed. All right, does that make sense? All right, great. And it turns out that zircons in granites from the Blue Ridge formed more or less 1 billion years ago. And these are among the oldest rocks in the Appalachians. And, they're not so far from here if you end up going a little bit to the west. Yeah, there you go. In fact, on this map, once again, oh, look at that. That is Montpelier, yeah. And all of the region that's shaded in this bluish color are basically rocks that are Precambrian, over 1 billion years in age. And so, again, the Blue Ridge in Virginia, I think, is special because it's got very old rocks that crop out there. There are some other weird ones that crop out in the Piedmont, but we don't need to talk about those today. Okay, so that was a long, long time ago. And this is one of the things that geologists like about archaeologists. We can kind of speak the same language when it comes to age in that way. But we take it even further, right? Billions of years, not necessarily just sort of thousands and hundreds of years. So we are a little bit to the east of that here at Montpelier. And I'd like to sort of focus on this map a little bit because we're going to sort of drive in, zoom into Montpelier. And this is a map I created for another presentation. But these old rocks of the Blue Ridge are called the basement complex. And the idea is they were originally on the bottom. And most houses that have basements, the basement is on the bottom. Checks out. And these old basement rocks have younger rocks that are layered on top of them. And Montpelier sits about right here on this belt of green rocks that is a geologic unit known as the Catoctin Formation. And it really is an important and exciting unit in the Central Appalachians. The other thing that I will point out, if you want to think about things, Monticello, as well as James Monroe's Highland, these are also located on the Catoctin Formation. So, coincidence, chance, and this rock has a cool history to tell you. It is a rock that is considerably younger than the basement rock, but by any sensible person's point of view, very old. All right, so we're going to learn a little bit more about the Catoctin Formation now. Here is a photograph of William and Mary students scampering over an outcrop along the Blue Ridge Parkway. And this is part of the Catoctin Formation, so the formatting's a little wonky there, but don't worry about that. What can we learn from this? Well, much of the Catoctin Formation is a metamorphosed igneous rock, a basalt originally that has been later changed, and we pretty well infer that it's a metamorphosed volcanic rock. Marina, can you hand out the two? Yeah, those. And it's typically fine-grained. It's a blue, greenish gray. And some people give me a lot of flack about it. They're like, dude, is this really green? Well, maybe it's green-blue or gray-blue, whatever you want to call it there. Some of the rock is pretty green because of the minerals that are in it. But there are structures that we can see in Shenandoah National Park and places where the Catoctin Formation crops out that really demonstrate to us that these are ancient lava flows. All right, so back in the day, the landscape in what would become Montpelier would have been covered by these thick, thick lava plains. And using a similar technique, we figured out the age of these. And they're on the order of about 550 to 570 million years. Really old, yeah? But half the age of the oldest rocks that we see in the Blue Ridge. The other thing that I think is important when it comes to thinking about the landscape, so the Catoctin Formation, a lot of people say, oh yeah, it's a greenstone. So here's a picture of my pocket knife. Here's an outcrop near Highland. And again, the rock is a bluish green gray. Typically, it's fairly hard. It's a metamorphic rock. But that rock sitting around in Virginia's humid climate weathers, and it weathers to a soil that is oftentimes a very orangey red, fairly high in iron and some other base compounds. So this is something that is oftentimes hard to sort of reconcile. The rock itself may be blue, green, and beautiful, but what happens to it when it gets weathered, it ends up looking like this. Although, again, these plantations were often sited on the Catoctin greenstones because this is a more fertile soil than much of the rock that you have in parts of the Piedmont, which is higher in acids, fewer nutrients that are associated with it. So bedrock gets turned to dirt, and some of that dirt is a pretty interesting soil. Okay, let's step back to deep time for a moment. It turns out when the Catoctin Formation was erupted, it was erupted over a very large area in the mid-Atlantic region. So this is kind of a fictitious but reasonable reconstruction of the geography when the Catoctin Formation formed. And these lava flows probably would have covered the ground from what could be southern Virginia all the way up into Pennsylvania, maybe even further. And we are pretty confident that these volcanic flows came out as we were breaking open a new ocean here. All right, so Laurentia is the cool name for the ancient part of North America, the old part. Gondwana is another important continental block. And lo and behold, these broke up at some point. And that breakup was the harbinger of that breakup was the extrusion of all of these lavas. And eventually that ocean, the Iapetus, would have covered or flooded much of Virginia. And if you go to the Shenandoah Valley, the limestones that you see there are all limestones that accumulated in that ancient ocean. Alrighty. So a little more on the regional scale here. Oh, what's the red star? All right, yeah. And like I said, when I created this map a long time ago, I was thinking about Monticello and other places. So sorry it didn't make it there, but it's got a red star today. All right. It can be easily corrected. But the Catoctin Formation, you can see it in southern Pennsylvania, Camp David, and Maryland. And then it occurs on two sides of a feature we call the Blue Ridge Anticlinorian. The western part of this is much of Shenandoah National Park, and the eastern part of this would be kind of the Blue Ridge foothills, the southwestern mountains. Charlottesville is right there. Oh, and Montpelier is right there. But there are really cool places where you can go and you can actually walk through original lava flows. All right. And Marina, I think that I forgot to hand out the big, wonderful, spectacular sample. The large sample that's going to go around now is actually from a cobble that I got out of a river near Charlottesville. But what you can see are these green and white specks. These are holes. And it's got a pretty cool story. That would have originally been that exhaled out of the magma. You had a hole in the rock as it froze, and then later it was filled by other minerals. In this instance, feldspar and epidote, and we call those amygdules. But that right there is primary evidence that these were once lavas. All right, and people who've really studied these things carefully have demonstrated in places there are 12, 14, 16 different major lava flows that make up the Catoctin Formation, and it sits on top of these even older rocks. Cool? And that is what has led to our campaign, Virginia is for Lavas. And I would say 9 out of 10 bumper stickers that I see have Virginia is for Lovers. But if you want one of those bumper stickers, let me know. When I come back, we will set you up with those, and we can see you going down the highway, and we will have a special bond that way. Okay, let me try to explain the third dimension, because I'm a structural geologist and I care about like the architecture of the Earth. So this is a geologic cross section. So that's the Earth's surface. And Charlottesville would be about right there. Shenandoah National Park would be right there. And remember, I said that we see the Catoctin Formation in two different places. This is the western limb, and this is the eastern limb, which is where we are here at Montpelier. And these rocks must have connected at one point, but they have been eroded away, and we exposed the older rocks in the middle. So the dotted lines are if you were connecting the geologic layers before they were eroded. Okay. Does that make sense? So at some point in time, we may well have had a Blue Ridge range, which would have been a much more continuous range and entirely underlain by the Catoctin Formation. Once upon a time thing, and that has been eroded. So Catoctin Formation has been eroded away there, and where it was is now been removed. Check. All right, and ideally over time we will continue to wear things down, and you'll see what's still preserved in the subsurface. But this overall kind of arch is what we call an anticline or an anticlinorian. So that's kind of the overall structure. And then the last thing I kind of want to get across about the Catoctin Formation, all of these rocks have been folded and deformed and transported from where they originally formed. So when the Appalachian Mountains were created, this is a continental collision that happened about 300 million years ago, plenty long time ago. The rocks of the Catoctin Formation have been shoved to the north and west, and all the rocks have kind of been squeegeed. And so, okay, this is Charlottesville, but originally these rocks would have probably formed in what is today much more like central and eastern Virginia, and that they were transported in this direction. Question? Correct. Made a big ocean. And then that ocean went bye-bye because we have a collision that gets rid of the ocean and boom. Aha. So the water is easy. It can move somewhere on planet Earth. Some of it actually may be subducted back into the deep interior. So when plates collide, some fraction of the ocean crust goes into the mantle. And it does take with it water, not like whole oceans worth, but effectively that ocean disappears, but the water is probably going to end up in another ocean somewhere on planet Earth's surface. Yeah, but that is a great question. So really here in Central Virginia, we've got an opening and a closing of an ocean basin. But wait, there's more. But let's just round out the Catoctin Formation before we go to the where's more. So I get questions like, where would you go today if you wanted to see something like the Catoctin Formation forming? And I would argue you should go to Iceland. It is not a perfect analog because they're Icelanders that are running around. They built roads. When the Catoctin Formation was being erupted, there were not people. But that is the kind of landscape where these lavas would have been flooding, 10s, 20, many, many kilometers and covering everything that is there. One of the things in the Catoctin Formation, we don't necessarily go find old volcanic edifices, and that's probably because a lot of the eruptions were coming out of these fissures. All right, these cracks that were tapping into the magma, and that the magma itself was so soupy that it flowed a long ways. All right, and it ran all over the continent. So if anyone asked you what Central Virginia might have looked like 550 million years ago, Iceland is a fairly reasonable analog. All right. And so the idea would be that, yeah, we were accumulating lava flow, and it would have been flooding the surface here and burying everything else that was there. All right. So I've got, I think, 2 more slides. I'm going to hand it off to Marina. But I want you to look at this map. Red star. Got it? These green areas here are actually some relatively young rocks that occur in Virginia. And these are what we call rift basins. And they contain rocks that are much, much younger than the greenstones. And in fact, the property here at Montpelier is in part on part of one of these particular rift basins. It's called the Barbersville Basin. And what's interesting about these basins is that in some parts of these basins, the sedimentary rocks that were deposited or formed there contain dinosaur tracks. All right, so these are young W&M geology students. I say that now because this person is now a full-fledged adult and a professor, and it makes me feel old. But near Culpeper in the quarry there, you can actually see dinosaur trackways, which is really cool. And they form in these basins of much younger sedimentary rock that we have here. And those basins basically formed, what kind of rocks would you find in them? Sedimentary rocks, things like conglomerates, sandstones, and mudstones. Marina has a mudstone and a sandstone and a conglomerate to pass around that came from nearby basins. And to give you maybe a third dimension picture, you could imagine if you have faulting and you're lowering a block of the Earth's crust, instead of creating a hole, you're creating a low spot in which sediment, and that would be the yellow and the pinkies, would be accumulating. And it turns out if you go this way at Montpelier, you're in one of these basins. And if you go that way towards the big house and up Chicken Mountain, you're in the greenstones. And those basins were the forerunner of the opening of the Atlantic Ocean. All right, so here is kind of a paleogeographic map. Sorry, that's not a red star, but it's a yellow one, and that's where we are. All right, but this would have been a young Atlantic Ocean about 160 million years ago. And these basins were the forerunner of the opening of that basin. And obviously, the Atlantic Ocean has gotten wider and wider over time, but the Western Sahara and Central Virginia would have been much, much closer prior to the opening of that. We had a question over here. Awesome. Awesome. So effectively, that is what I wanted to say to you guys. And I'm going to get out of the hot seat. And Matt's going to kind of flip the presentation, but I'm happy to take questions while Marina comes over to get rolling with her stuff. So. That's right. So another way to think about it is effectively the faults were starting to rip the continent apart. And before it completely ripped it apart and you made ocean crust, you had these downdropped areas of sediment in. That makes sense? Yeah.
Randy, you should be set.
Okay, so you heard all about the Catoctin and the regional geology. I'm going to focus in on specifically the quartz. So first of all, I want to express my thanks for being able to work with these quartz crystal artifacts. It's a wonderful thing that W&M Geology can collaborate with both James Madison's Montpelier Archaeology Department and the Montpelier Descendants Committee to understand more about these quartz clasts. But first off, what is quartz? I'm talking about all these crystals, but what's going on? It is one of the most abundant minerals in the crust. And the main reason for that is because you have a high abundance of both its main constituents, oxygen and silicon, in the Earth's crust. So that allows for the formation of lots of quartz crystals, and because they're so resilient, so the way that the silicon and the oxygen bond is in very strong shapes that allows the quartz to kind of stick together even through tough times. That's why you're also going to see a lot of quartz around you and in life. But let's think about how quartz can appear differently. So first off, you could have really clear, beautiful quartz crystals, as Chuck has one of the samples there. So you could have really, really beautiful, pretty quartz. Yes, oohs and ahs, very exciting. But what you see more commonly, and this is more similar to the quartz crystal artifacts, is quartz where you have a lot of cracks or dislocations within the quartz. So it's going to be a little bit more disorganized and won't be as clear to see through, but can still form nice, lovely, huge crystals. And then finally, you're going to see it. Oh, I forgot to gesture towards the less exciting, not clear quartz. Thank you, thank you. Yes, let's celebrate it as well. And then that final piece is another sandstone, but this one has less hematite staining or like iron in it, so it would be less red than the other sandstone Chuck passed around. So it's from kind of like a beach area, less exciting tectonics going on with it.
But still quartz.
But still quartz. Still lots of like tiny little pieces of quartz. So then talking about veins, and oh look, the Catoctin greenstone has reappeared for this discussion. Basically what happens is as we're having that cooling of the lava, you can have some cracks form, and that's where new minerals can grow and cause like the quartz to grow in there. And we sometimes call that recrystallization because you have that first wave of crystallization with the rock itself. And then the quartz is like, oh, I can snuggle in right here. And my research questions for this particular project in talking about how the quartz may have done that here at James Madison's Montpelier is what processes were involved in the formation of quartz at the site, both as the quartz crystal artifacts and then within the Catoctin greenstone and the surrounding Culpeper Basin. And both of those, as you just heard about, are kind of that Triassic and then the Catoctin all the way back in 550 to 570. So kind of understanding when it might have formed is going to give us more about that story. And then also, did it form from that local bedrock, or was it transported to the site by another way? And that would give us information if maybe there was human transport, maybe geologic transport. There are a lot of questions we can look into geologically to maybe make some anthropologic questions, give some anthropologic answers as well. But let's look a little bit more into how it forms in veins, because when I got one of the samples, this is one of the most exciting. So you can see the archaeological label there on the left, and then my label to simplify it a little bit, because it's very important to know all of that archaeological information. But for me, it's just my sample one. So you can see lots of tiny little quartz crystals. I'm pointing at the screen and that's not helping anyone. Lots of tiny little quartz crystals down here. And then these are the larger quartz crystals as it continues to grow. And that gives us a sign that it may have formed in a vein, because one way that can happen is we have the little space in the rock. It may be cracked as it was cooling or coming up to the surface. Then we have some fluids flow through, and that can include some water and some of that SiO2 or quartz. And with a little bit of that, and just a small amount of space, the quartz crystals are going to get all tangled because they're all fighting each other to be able to grow, be able to make it into that space. So they're doing that, but then we might get an opportunity for maybe some more cooling, maybe some more movement up to the surface, and that vein space can, book, expand. And if we have a little bit more SiO2 in the water as it continues to grow, the quartz is like, oh, I can grow huge, exciting, really cool ooh and ah crystals. So, boom. And that's kind of how that pattern may have occurred for this one artifact. So, but how do we interpret what fluids the quartz is forming from? So I'm telling you about all of this water that's moving through, but where is it coming from and what's going on? So one of the ways we can take that same sample, think about its fluids, and think about that formula. And in particular, we're going to focus on the oxygen. So oxygen has isotopes to it. So it can sometimes have different numbers within its atomic structure that allow it to be lighter, or oxygen isotope 16, or heavier oxygen, or oxygen isotope 18. And what we can do with that is do something called delta O18 oxygen isotope signatures. And basically, that takes the ratio of the heavier oxygen over the lighter oxygen. So if we put it on a fun little graph here, we can see that in precipitation, we're going to have a lot more of the light oxygen. We'll get that pointer ready. A lot more of the light oxygen, and that ratio is going to be negative because there's no heavy oxygen up top. Then as we get into ocean water, there's going to be more of a balance between the light oxygen and the heavy oxygen. So things are going to be pretty even. But in the rocks we're excited about, in that magma, we're going to see kind of just a little bit more heavy oxygen to light oxygen. And then in both sedimentary and volcanic rocks, we're going to see even more of that heavy oxygen because it doesn't want to move around. It wants to stick close to the ground. It's heavy, it's tired, it wants to rest. So then kind of giving you guys a progress report on what I've been doing with these quartz crystal artifacts, these are my methods to date. So the first thing was to do that relabeling as I showed off with that first image. And then second was to create some 3D scans of the quartz crystal artifacts so that when we cut them, we could still see what was going on in the whole crystal. Then we made some molds to be able to hold the quartz crystals in place. And finally, we made some cuts to create the slabs for later detailed analysis. So to go through more specifically, I have both a naming scheme and a color scheme, and that way I could keep it clear between the archaeological labels, keep pointing at the screen, archaeological labels and my personal labels, and that way we could make sure to match the artifacts when we're returning them here, and these are actually the artifact bags themselves right here. So very exciting. And then the 3D scans, this might be another ooh and ah moment, we'll see. We were able to get, using Clem's phone actually, scan. Yeah. And you can see that that Sharpie mark there is actually where we marked out the cut to be able to cut through that crystal. So what we did next, it wants to continue to spin. What we did next was create molds to be able to hold the quartz crystals in that exact orientation to get a really straight and clear cut. So you can see here, that's the exact straight edge that went up against the saw guide. And then this is the arrow pointing to which direction we were going to feed it through the saw. And then again, keeping those labels continuous to make sure we're documenting it all. And then finally, we got to the really fun and exciting part, which was cutting it. So this is a saw where it's more of a grinding saw instead of like a sharp blade. So it's safe to have your hands that close to it. And this is that first really exciting sample. Don't get me wrong, I love all the little quartz samples, but this one was definitely our most exciting because of the structures. So we were able to get a slice that's right down the crystal. So we can see like, oh, maybe there's some smaller stuff here. And oh, look at this line. What change could be happening there? And then this stuff up at the top. So that was an area for exploration. And then next, we also took a slice through our second sample, same thing, looking at all these different crystal structures here. Our third one, we took a slice through an individual crystal, and you can actually see the little hexagonal structure of this particular quartz crystal. And what that's going to help us understand is basically how it grew over time. So it kind of grows both upward and outward at the same time. So we're going to see in 3 dimensions how fluids might have changed. And then finally, for O4, same thing. We were cutting across this one crystal to be able to get an understanding of how it was growing over time. And then, as I told you, this first sample has returned because we have some exciting information about it. So this is specifically the slice all on its own in a fancy camera box, being showcased here. And we were able to send off some of the slices to be made into thin sections. And that's what this image is here. So you can see all of the individual crystals. You can see like here, it's kind of like vague that there might be a lot of crystals, but then in the actual thin section image, you're like, whoa, exactly. So many crystals. And what this also allows us to do is look at features between the two. So you can see this line between both of them, and that's an area where we might have some fluid inclusions, which could give us a really exciting opportunity to look at the temperature at which the quartz formed and tell more of its story that way. You can also see that the crystals match up to one another. So when we're looking at further information for the oxygen isotope information, which involves us drilling into this slab on the left, we want to make sure we're drilling the same area we're looking at in thin section and seeing interesting things happening. And then finally, there's a gap here, and we want to understand what happened with crystal growth to cause this little gap in the crystal. What was going on in the quartz? Why did it not want to particularly grow there? So lots of mysteries. And then to be able to make the story of the quartz even clearer, we're going to be doing some imaging, and that's going to allow us to look at the quartz crystal in different colors of light to see like how those growth rings are happening and what's occurring within the quartz itself. And then that oxygen isotope analysis I was talking about, what we're going to do is take that mini slab you saw with sample 1 and grind it down into a little powder. And then a machine is going to be able to use laser chlorination to figure out what's going on. So yeah. That is the story of the quartz. Thank you so much. And please feel free to ask any questions you may have.
So just because just think about theories, what could possibly happen? Do you have any theories of what happened? Is it fun?
So our main one is kind of that this is quartz that's formed in a vein, but one of the interesting things on the bottom of sample 1 is that it looks like it has some of the rock that it grew from on the bottom. So we're trying to kind of figure out what's going on there. I can pass this around as well. So you can take a look at that. And it looks to be more like a sandstone, but we don't really know yet.
Do you have any assumptions on what happened at that gap?
I definitely think there's a difference in like fluid pulses that cause that, but I'm not really sure specifically what's happened there yet. That's going to be more like once we do the oxygen isotope analysis, we're going to figure out like, oh, this came from this specific fluid pulse versus another one, and kind of to understand what's going on. And what we're also going to do is try and match that analysis to the surrounding rocks, so the Catoctin greenstone, and also those Triassic basins to figure out like, did it form from these rocks or did it form from elsewhere? Yes. Any other questions? Yes.
Can you elaborate a bit more on why you became interested in studying the quartz from Montpelier?
So one of the main things that happened is when we came on that trip, Matt was showing us the quartz crystals, and I was like, "Ooh, this could be like a story I could tell with the quartz to kind of understand more about what was going on behind it, and to know that there's also some anthropological connections." I became really excited to understand how to connect geology and anthropology there. I'm a geology and English double major, so I really like hearing human stories and geologic ones and kind of finding connections between them. Yeah.
Marina and Chuck, this would be
Yes.
for both of you all. It's the quartz that you're sampling, Marina, is in the geologic topsoil. So it's in the soil that is part of all this erosional stratigraphy complex. Is there any way, like, what are the chances of like how high with all this soil? We were talking about this when you all last visited, what the rates of soil erosion are over time. Like, and you all were pointing out with that one rock that it looks like it could have a sandstone base.
Yeah.
And this is all greenstone. How high up could that quartz vein have originally been in relationship to where we're standing at the memorial site today? 100 feet up, with all this soil eroding down, and how long do the rocks remain in place? Like these quartz never decompose, while the greenstone decomposes and are absorbed by plants or get washed out with a major flow. Like how many feet of quartz could we have accumulated in this topsoil? Because it's like, what's it called, a gravelly layer or an armored layer. And maybe
Well, I think what's unusual is that you do, accumulate quartz. You have a volume of rock that has been eroded away, it has been weathered away, and that the quartz is fairly insoluble. So you'll end up concentrating that, and so you may have pebbles and stuff like that on or near the surface. But I've almost never seen that as these crystals. What you typically see are, ugly quartz, as opposed to pretty quartz. Maybe I can couch it that way. which is why I'm sort of, I really do think these samples were placed there as opposed to that they formed there. And so really one of our questions is, are they forming in the Catoctin formation, or are they forming potentially in the basin rocks? And that they have been found and quarried somewhere because they're cool looking, and then they end up here. I mean, I guess one possibility is that they do originate there, and they've just been, they are left over, and because they're quartz, they're more resilient. My suspicion is there are somewhere in the area there are veins in which these are preserved in. And part of what our job is going to be is to go sample rocks in the basin and Catoctin greenstone, and then actually see do the isotopes match? Is it different in the basin than it is in the greenstones? The greenstones were metamorphosed, the basin rocks weren't. So when we're done, we should have isotopes from the basin, isotopes from the Catoctin formation, and isotopes from the quartz artifacts. And which are they more like?
The other part, it's just to finish up on that. The other part of the quartz, we've got most of the quartz we recovered from these units isn't quartz crystals. It's the ugly quartz you're talking about, just the base quartz. And I don't know if there'd be a way to test the base quartz that, certainly wouldn't have had any, there would be no reason to have a deposit there against the vein quartz to see if it's similar when it gives conclusions.
Yeah, and I mean, most of the time in the Piedmont, the quartz that you see in the soil, it was in a vein at some point. But it wasn't necessarily a vein that had ample space to grow crystals. But that's exactly what we want. We want to collect quartz in situ from other places and then compare it to the art. Question? Oh, yeah.
Yes. So it actually, does anyone have the one slice you can pass around? Awesome. I can kind of show you a little bit on the rock. So it had to be thick enough so it wouldn't just like shatter and fall apart. So it was basically like on here, maybe about that thick for the mini slab. And you can see a little bit of a sense of scale with this photo. Let me get back to it. So this is maybe like a little chunk of clay about this size. And then you have the rock itself. So it was a cut right through. We also kept this block that's right here for further like analysis. So it's a pretty sizable chunk, but we tried to leave as much as we could of the artifacts to be able to have them for reburial. Any other questions?
I have a question.
Yes.
So I know you said that these form or talking about that you kind of analyze and kind of rock, what you don't know yet, kind of actually it. What happened to them? Did it like
That's
just mineralize?
Ashurkoff. Hi.
that's more.
Yes.
Oh, yes.
Geology.
Yes. Okay. So basically we're not quite sure. This is going to be more like analysis of it. Because like quartz crystals in and of themselves are so strong and resistant to erosion, it is possible that the rock beneath it did erode away and break down if it was something weaker like the Catoctin greenstone and it became like the Udisol, like Chuck was talking about.
Yeah.
But we don't have any evidence for that either way at the moment. So it's more continuing to explore and continuing to try and figure it out.
Okay, one last question.
Yes, absolutely.
When it comes to the vein,
Yes.
it's possible that quartz can be beneath it.
Oh, like if the quartz is growing from this direction, it could also grow from this direction down. Yeah, the quartz, it depends on like where the fluid is flowing from. But if you have like some of the silicone get the SiO2 get deposited up top, it can grow downward as well. It's more likely for it to grow up gravity-wise because it's going to be easier for the crystal to form, but it can do whatever it wants and have little adventures. Yeah. Yes. Okay.
Sakina, you had a question? You could unmute, Sakina.
Yes, I'm I don't have all the scientific words to use, but I was wondering after the collision of the plates, how high did the area of Montpelier rise?
I think that's more of a Chuck question than it is a me question. It's not quartz related, so I'm going to hand it over to our structural geologist.
I can't be heard.
I will repeat. I will, yes.
So that's a great question. We know that when we effectively collided Africa with North America, we created a big mountain chain, and we call those the Appalachians. But we don't know the absolute height of what they were. However, we can play some guessing games, and it's pretty clear that rocks in the Piedmont have been very deeply, which means you have to have a big pile of rock on top of them, and you can then guess how thick your mountains would be. So I think would be safe to say that the Appalachians would have probably been a Himalaya-sized mountain range, but that would have been 280 million years ago. Right. And so when I say a Himalaya-sized mountain range, some areas in this region might have been as high as 15 to 20,000 feet above sea level, no problem. But we also think that almost all of that was eroded away, and that there has been reinvigoration, so that the modern Blue Ridge Mountains aren't the little nubs of what used to be great. They're actually rejuvenated, and that's probably because they're hard rocks and weak rocks, and there are forces that have caused them to uplift. Actually, changing climate may have played a role. But yeah, the rocks at Montpelier might well have been at very high elevation 280 million years ago. And that's one of the games we like to play. Can you track through time how rocks have gone up and down relative to, say, sea level?
Mm-hmm. Were you able to hear that, Sakina?
Yes, I did. Thank you.
Awesome.
That's the teacher voice.
Curious. Any other questions? Awesome. Okay.
Oh, I'm sorry.
No, you're good.
Where might this quartz vein be on the property? Do you know exactly where it may have? Oh, you have no idea.
No, that's what we're.
That's the mystery. That's the exploration. Yeah, that's all of the questions you've been asking about, kind of the deeper story, are exactly the questions I'm also asking to try and understand what's going on.
Or in an old piece of literature from the Catoctin Formation, this is a report from the 1940s, that near James Monroe's Highland, they widened the road in Albemarle, and they cut through the greenstone. And in doing so, they actually cut through some veins where you had good quartz crystals that were actually amethyst. So it was much more purpley than the white. And that is the only report we've ever seen. And I am old enough, and I wander around and see a lot of rocks in Virginia, and I have never stumbled upon this in my comings and goings. But our idea is we want to walk around, go find outcrops and see what we can see in the veins in situ.
So if we know there have been locations where when we hit the subsoil of the horizon, or they're linear veins, if you will, in situ quartz, if we have those pictures and their location and GIS, want that information?
Oh yeah, I mean, we would love to spatially analyze what you guys had excavated already. And I think the first time I was here and we were talking about that when everything was exposed there, it's I would love to see that on a map. One of the things that Marina and Clem and Chuck have been doing is we've been drawing lines on the digital elevation model.
It's in that folder.
Oh yeah, it's in the folder.
Out. Yes.
And you too could draw these lines if you want. But the idea is these lineaments that we see on the landscape, they may be the reflection of fractures and veins. And so this is just one way to sort of get at it, hand that around. And so each line we draw, it may or may not be anything meaningful. But it would be cool at a different scale of your excavation to trace what you've already seen and do those patterns map to that different scale.
One thing we might want to do, maybe even for next week, is I think you all saw this. We revealed more after you all left. Is one of the units we had open at the memorial site. There's a quartz vein, and we found in situ quartz crystals.
Yeah, there was 2 rows of greenstone. And then in between the 2 rows of greenstone, there was very fragmented quartz, and we dug into it a couple inches and got quartz crystals from that too. And that was that subsoil.
So what we were finding in the excavations is we were finding quartz crystals in the subsoil that had never been disturbed by humans whatsoever, finding the quartz crystals. And then with the accumulated, well, all the quartz that accumulates in the topsoil, like if you go to our units today, there's way more quartz in the topsoil than there is in the underlying subsoil. So that's where we were, wondering these quartz crystals, they accumulated. So probably, if anything, we're imagining that based on this area being plowed for, well over 100 years, there are quartz crystals, larger ones that were found visually, seen by the enslaved farmers and were taken away. But then these tiny ones, were just, they wouldn't be too small unless you're crazy like us and you're screening through a quarter-inch screen or doing, washing through the window screen, looking for these things that would never be seen.
Right.
So that's where, and this is a really cool, using different disciplinary questions to approach the same question. Are these anthropomorphic, origins of these quartz crystals at the site, or are they natural? And there's certainly human-made processes of plowing, and the amount of erosion that happened over the past 100 years during, from the 1720s through the Revolutionary period is probably more erosion that occurred than in like 1 million years of soil loss, just naturally. And so there's probably an accumulated rocks that were from that plowing episode of like 75 years. So this is like,
I mean, certainly
super
from what
fun.
you guys are reporting, it may well be that these are more or less in situ, which would be cool, which means you are sitting on top of, those veins more or less. And one of my hypotheses is to make these basins, these Mesozoic basins, you have to fracture and crack the existing crust. And so it may be that we have veins in the Catoctin Formation, but the age of those veins is actually Mesozoic when we were forming the basins. But again, we need to see stuff that's in situ.
What's the million years on the Mesozoic?
200 million. Yeah, so like I said, I'm very flippant with the use of millions of years, but the Catoctin Formation lava is at 550 million, and then those lavas were hardened to rock, they were buried and metamorphosed, and then they were back at the surface 200 million years ago, and we know they were at the surface 200 million years ago because they are contributing blasts into the rocks, sedimentary rocks now that are of that age. So again, the Catoctin Formation formed at the surface. It went down and got turned into a greenstone. It came back up to the surface by 200 million years ago and may have been slightly buried again. So you start thinking about yo-yos for time.
How deep were the greenstones when these quartz, how does the quartz, is it only under intense depth, heat, and pressure that the quartz gets deposited, or is this like 100 feet from the ground surface, or what is that? You all know?
I mean, quartz is a pretty actively forming mineral. It's going to form wherever it has the space. It's, if I'm remembering properly, I'm looking to Clem, who's our petrologist. Quartz has a pretty large range of when it can form and kind of when it also deforms and slips.
Yeah, they have over a wide range of temperature. So if you were to try to grow a quartz crystal in here, you might have to stare at it for longer than you can live. But one of the cool things is the hotter it gets, so instead of being room temperature, maybe it's 400 or 500 degrees Celsius. I don't know what that is. The time it'll take to grow that same size crystal is going to be a lot smaller, because when there's lots of heat, the heat provides energy for the atoms to move around, so it competes. So there are ways that we can look at the quartz crystal structure and other things inside of it, try to figure out what the temperature was when it was formed. And if you're thinking of quartz forming in magma, for example, those temperatures are going to be way higher. Think about 800 to 900 degrees, 1,000 degrees Celsius. But if you're forming them in these hydrothermal veins, those can start forming at 200, 300, 400 degrees Celsius. So typically a lot more shallow. So then you can start thinking about, once you know about the temperature, at what kind of depths to experience those temperatures. So quartz is one of these minerals that can form at such a wide range of conditions, but the temperature and depth at which that's happening can really speed up. So if you think of having really big crystal, there's got to be something that drives the growth of that. So pretty significant. And that can be temperature. It can also be how much silica is dissolved in the water to provide that silica nutrient to grow crystal.
Yeah, so hopefully in 6 months, we could give you a better answer.
Yeah.
But for these, are we talking 100 feet, 1,000 feet?
I would say not 100 feet.
Yeah.
But thousands to a few kilometers.
Oh, wow. Wow.
Yeah.
That's cool.
And that kind of what Clem was talking about with also like changes in the availability of the silicon and also the temperature, that could be why we're seeing differences in like the crystallization. Like we're seeing like, oh, tiny little quartz crystals down here at the bottom versus like much larger ones as we go up. So we're kind of tracking those changes. Yes.
Oh, big question. So no assumption that all of this quartz is being formed in the same conditions at the same time. There could be potentially like this is growing liquid formation or whatever, or like it's supposed to be here, and then temperature changes, different types of crystal. Okay.
Yeah.
Yeah,
So-
so that's why it's going to be important for us to sample quartz from like clearly the Mesozoic basin and
Mhm.
clearly in situ in the Kentucky greenstone, and then compare that to what we found from the art.
Perhaps this is going through the information. I think I can answer my own question, but I just want to pose it anyways.
Mhm.
Other than actually digging in and finding important things to do, are there any other ways to remotely sense it, or is that just not? Is that beyond one?
So quartz isn't particularly magnetic with just the silicon and the oxygen. But there are like, I'm trying to think, because using like, it depends a lot on the soil. So like if you use GPR of like that ground penetrating radar, which you guys probably also use for archaeological stuff, you can like look through and see all of those cool things. But with clayey soils, it tends to yes. So you guys already know this, how there's that. So that's one of the main reasons we wouldn't end up like seeing a lot of quartz remotely sensed. But it's definitely something like if there were like larger chunks of quartz and like maybe it's in an area where most of the other rocks are magnetic, we'd be able to say, oh, it's not magnetic, maybe it's some quartz that's around here.
Yeah,
But-
if we had like 5-foot quartz crystals, we would have a better chance.
Yes.
Remotely sense them. But when you're talking about this size or smaller, it becomes hard.
Mm-hmm. Yeah, go for it.
Just- Right, you know, there are people going to these caves, water caves,
Mhm.
and I look up and there's like crystals all over.
Mhm.
Is that a real thing? And then is that kind of what would that look like? Like in the, how is that possible?
So are you thinking of like stalactites and stalagmites in caves?
No idea.
Okay. So yeah. Yeah.
Is that possible? And have you seen those in this region, especially because there's been collisions and shakes and it's a time thing?
I think the karst topography around the area, it's usually more like calcite, because that's like more limestoney calcite material. So that's basically like what you would see from like if you ever looked for like little shells and bivalves, that's mainly what they're like made of and what their substrate is what like surrounds them is going to be. And that's a lot more times what you see with cave systems where you get that eroded away by water, because limestone is a lot more water soluble, unlike quartz where it's like it's stuck together. Silicon and oxygen aren't particularly like chemically active. They want to stick where they are. So you'd see like more cave systems with like what I was saying, stalactites and stalagmites from that erosion and the processes of water flowing through. So you would get like crystals growing down from the top and crystals growing down up from the bottom due to like that recrystallization from water flowing through and also like carving out that area. But you can also get some really cool caves where you have a bunch of crystals growing on top of each other. In fact, in Clem's minerals class, she has a picture. Yeah.
Basically, like I think
Oh my
Yeah.
Completely real.
Uh-huh.
Yeah,
Yeah, I'm gonna be the big downer here.
Yeah.
If Matt and the team decided to dig a big subterranean cave failure, and you all of a sudden had that, and you let fluid flow through it, you're not gonna make that. And you're probably not gonna make that here because there is silica dissolved in the natural water here, but there's not that much silica. Why? Because it's fairly insoluble at Earth's surface temperature. If you ask them to dig a much deeper hole and you're able to bring up really hot water, you may have more silica. All right. So I think what you would end up with is your cave would be barren of that because of the local geology here. So for us to probably make these veins, you were tapping into waters that had been circulating deep enough to get hot and have enough silica in them to really grow crystals. Whereas today you can dig a hole and probably not going to grow much very quickly.
Though, can this happen closer to like Norfolk where there is like water sources, like closer to the Atlantic?
I think it would be kind of the same problem, but it'd be even worse. Where we are in Williamsburg, we would dig a big cave and it would collapse on itself. It's not solid. But if you wanted to do that, I would go to the Shenandoah Valley and you could dig a hole there, but you're going to make the cave formations of those crystals are going to be calcite. So it's going to be calcium carbonate, not necessarily silver.
So if you want to see that, Chuck advocates that you dig a really deep hole and let some very hot water go through.
But also that cave had to form over probably hundreds of thousands of years at really high temperature. And to keep the water that hot without it turning to steam, you also have to bury rocks below the surface so that the pressure kind of condenses the steam that enters the water. So they're not very like human friendly.
Thank you for going
There are caves on the west side of the Blue Ridge Mountain, and there are sometimes reports of little janky caves in the Piedmont region of Virginia, but mostly the rock is the wrong kind of rock to make cap.
Well, let's give a big round of applause. The results of your
Yeah, I will continue to keep you posted. This is just a progress report, so more to come.
time to see this. We're gonna go back up.
In our unit, we have like a big.
I'm very excited about seeing that. That's that would be very good.
Yeah, we know you haven't better.
Yeah.
Time for that. Hey, thanks everybody on Zoom for joining us. Bye, Sakina.
Bye,
Thanks for the
thank you.
questions, Sarah.